Alright, so I got an email request this morning for question 63 on the homework, and let's bring it up on the desktop. So the question here is, identify the more stable stereoisomer in the following pair and choose the reason that explains your choice. So it gives you one where you've got two methyl groups. So we've got a 1,3,4 trimethyl cyclohexane, with the 1 and 3 positions being cis and the 4th position being trans. So to answer this type of question, let's bring up the whiteboard and let's look at the position. So the thing about methyl groups is that we're going to hydrogen groups, so preferably we would have all these groups in the equatorial position if that was possible. Make sure I have my chat up so this way if anybody asks questions I can see it. So let's see here. I know I got a marker somewhere. I thought I did. Where are you? Just really don't want to do this with a magic marker. Looks like I might have to. Oh, nope, got a green one. So you've got cyclohexane, and we're considering the 1, 3, and 4 positions. So the way I would approach this problem is I would say, okay, ideally I want one that maximizes the numbers that are in the axial and equatorial. So the thing is that we can interconvert between axial and equatorial. So basically we want as many in the equatorial position as possible. So basically we want one that puts as many of these having the same relative positions to each other. So ideally we'd have all 3 positions equatorial, but if not, we want to have like 2 that were equatorial and 1 that was axial. So let's start with the first position. And let's say we took the first position and we set it as axial, recognizing that we can flip back and forth between equatorial. Well, if we have a cis here, this would be equatorial. If this was cis, it would be axial, and if it was trans, it would be equatorial. For this one, if it was cis, it would be equatorial, trans would be axial. But again, keep in mind that we can flip these. So this gets flipped to equatorial, this would also be equatorial, or in the trans position it would be axial. So if we look at our options here, oops, sorry. Oh, seriously, you're going to do this to me midstream? So we go back to the desktop. We have 2 positions. So we have the first one where we have relative to the first, first one's cis, one's trans, cis. So if we look at our 2 options and we go back to the board here, in the first one is cis, which would make them both equatorial if they were equatorial, and the second one is trans, and the trans would also be in the same position. So if we go with the first one, where the first one's the third position, third position is cis, the 4th position is trans, all 3 would be axial or all 3 would be equatorial. So that gives us the ability to put all 3 in the equatorial position. If we switch to the other one, we're going to have 2 that are together, so 2 that would be equatorial and 1 that would be axial. So when it asks you for which one would be more stable, it's going to be the first one. And the first one's going to be more stable because all methyl groups can be in the equatorial positions. So if we say first structure A, all 3 are equatorial in the most stable conformation, this ends up being correct. Now for the other one, we're going to have 2 methyls that are equatorial and 1 that's axial in the most stable conformation. But that does put 1 in the axial position, so it's not as stable as one that can put all 3 in the equatorial positions. And each of these explanations get progressively worse. So 2 methyl groups are axial and 1's equatorial. This is less stable because you've got 3 that are sterically hindered. And if all 3 methyl groups are axial, they're not, like, they're going to destabilize. It's going to be super unstable. So that was the first question I got. Now, I just got a question in the text box. Can we go over R and S notation on the study guide? So let me bring up the study guide. And do you have a specific question, or you just want me to work through like the first few? For the first few, okay. Okay, so for the alkanes, R and S is actually going to be the hardest because everything is carbon or hydrogen. So this is definitely one where you're going to have to like work through to see what the successive bonds look like. So we'll work through the first two. Now these are nice because it's really obvious where the chiral centers are. They're the only places with the wedges and the dashes. Not to make it easy for us, just those are the only ones that really mattered. So if we have the first one, and we've got that coming out, so we have the alpha group, and that one going back. And we want to do the R and S for this chiral center and this chiral center. So let's do the first one. So we've got 4 groups. We've got a hydrogen, and this is going to be our lowest group, number 4. And we've got each one bound to 4 carbons. So if we look at it, we have a carbon. We'll write what's bound to those carbons. We have a carbon, CHH, carbon, CHH, carbon, CHH. So the next one out doesn't really tell us anything. They're both methylene groups. So now if we go further out, we get a CH3 group, which would be C with 3 H's. We get a C, C, H, and H. And when we go further out, we get a C, CCH. So we get a methine and a methylene. So a methyl group ranks lower than the methyl group ranks lower than the methyl, which ranks lower than the methylene. So the methylene is going to be the highest group, so it's going to be this direction is going to be number 1. This is going to rank higher because it's got the methylene group, and this is going to rank 3rd highest for the methyl group, and then the hydrogens in the back. So if we look at this, this is clockwise rotation, so this one here is going to be an R on the one side. This side, same line of reasoning. Hydrogen is going to be the lowest. We have a CH2, CH2, CH2. We go further out, CH2. This ends up taking higher. This direction ends up taking higher priority, going counterclockwise. We're still both at CH2s. If we go further out, this hits a methylene group. So this would be the 2nd highest priority. And the methyl group will be the 3rd highest. So it looks counterclockwise here because we have this wedge bond. Hydrogen is actually coming at you, so we'd have to rotate it. And if we rotate it, it would be clockwise, so this would be a 2nd R group. So to figure out the priorities with these alkanes, easiest thing to do, methyl group, okay, hydrogen's lowest, methyl's second lowest, methylene, a CH2, is 2nd highest, and then a methine, okay, sorry, backed up. Hydrogen's the lowest. Next up is the methyl, the CH3. Next up is the CH2. A CH with 3 carbon bonds, and then a quaternary carbon, one that has 3 carbon bonds, would be the highest ranked. So what you do is that you start working your way away from the carbon you're looking at. And we look for the first point of difference. So they each connect to a CH2 group, doesn't do us anything. This connects to a methine group, 1 hydrogen, so it'll be the highest priority. This is still a methylene and methylene. Next one further out, this is a methine, that's a methyl. Methine ranks higher. The next one. And do understand, like, alkane RS is just the absolute hardest because there's no atomic weights that really do you any favor. You have carbons and hydrogens, so it's actually easier to go off of the nature of that CH group. If it's a methyl, if it's a methylene, a CH2, if it's a methine, a CH, or if it's a quaternary carbon with 3 carbons bound to it. So if we go to this one, I'm sorry, I only have one color pen right now. And let's start with the top one. So if we start with the top one, hydrogen's in the back. This makes it easy. We've got CH2, CH2, doesn't tell us anything. We've got a methyl, and a methylene, and a methylene. So this is going to be the third lowest priority. When it comes to these two, if we look out, this one's bound to a CH3, this one's bound to a CH2, so this ends up taking higher priority. So this ends up being 1, this ends up being 2. So if we go 1, 2, 3, that's counterclockwise. That's S. For this one, we've got a methyl, a methylene, and a methine. So methyl is going to be the third lowest with hydrogen in the back. Methylene is going to be the second highest. The methine is going to be the first highest. Because it's wedged, we can treat the hydrogen as being in the back. So 1, 2, 3. Counterclockwise gives us S. The last one, we've got a methylene, and a methine. So that's going to be the highest priority right there. As we go one out, it's a methine, that's a methylene. So this is second, and this is third. 1, 2, 3 is counterclockwise, but because we got a wedge, we can reverse it, so this will end up being R. Now, you won't see anything this hard on the exam. These are particularly hard questions. It's probably just going to be one chiral center. But it's going to follow the same line of reasoning. You're going to start drawing yourself out from those carbons, and the first point of difference, you're going to compare it. If it's carbon bound to 3 carbons, it's the highest priority. If it's a carbon bound to 1 hydrogen with 2 other carbons bound to it, and this is as you're moving out. So if you end up with a methine, that's second highest priority. If you end up with a methylene with CH2, that's third highest priority, and then methyl is the lowest priority of things bound to carbons. And again, hydrogen is going to go in the back. So something ridiculously hard. Be something like that. But again, you would never get anything that hard. So any questions about the R and the S? It is very hard for alkanes, and if you can get through R and S with alkanes, alcohols, alkyl halides get super trivial. But that's why we're teaching the course this way. First hard punch was the analysis, second hard punch is going to be the naming with the R and the S, third hard punch is going to come on the next exam when you start doing reactions, and after that, if you can do test 1, test 2, and test 3, you're set for 4 and 5, and honestly probably through organic too. The boat and the skew boat. So with the boat, so if you take the boat conformation, the best thing I have here for you is a sheet of paper. So basically with the boat conformation, we've got our plane of carbons. That won't work. So we've got our C6 bond, and then when we do boat, we turn up opposite corners. And so it takes this shape. Now, what doesn't come across in the line bond drawing is that there's 2 hydrogens sticking off these carbons and they're pointing at each other. So with skew boat, what we actually do is we take the plane of the boat and we turn it. It's kind of hard to do with a sheet of paper. But when we kind of warp it, so this way the corners aren't actually across from each other, they're actually tilted off axis, this puts the 2 hydrogens away from each other. So a skew boat is a slightly more stable conformation than the boat conformation. But the reason why I say slightly is that in order to distort that boat, in order to turn the corner, basically these corner carbons out of plane, you're stressing the bonds to do that. So it's a trade-off between sterics and bond angle. And again, skew boat and boat look pretty much the same. It's just with a skew boat, you're going to take the two corners that make up the bond of the boat, and you're going to kind of like turn them off axis to each other. And this will take the two hydrogens that are axial and pointing each other at the top two carbons out of playing with each other. Other questions? Yeah, it's even hard to draw it because when you draw it, you kind of draw the bonds distorted, but it's hard to tell if the bonds are distorted because you're showing a skew boat or if it's distorted just because you're bad at drawing it. Resonance structures, we can do that. All right. So when it comes to drawing Lewis structures, that double arrow has a lot of meaning to it. So that's the first problem on the homework. So we've got carbon, H, oxygen, hydrogen. So resonance arrows can do a lot of things. They can convert a lone pair into a bond. They can convert a bond back into a lone pair. Honestly, that's the big thing they do. So in this case, we have a line drawn between the two. So when we draw this line from a double bond to something, what we are indicating is that we are creating a bond. So the end result of this, sorry, but I'm drawing it sideways, is that we move the double bond. Now, when it comes to double bonds, we can't change the net charge. So, or when it comes to resonance, we can't change the net charge. So we have a positive charge, and this positive charge here comes from the formal charge. So to calculate formal charge, it's the number of valence electrons minus the number of lone pairs minus the number of bonds. So carbon starts with 4 valence electrons. It has 3 bonds when we start. Subtract 3, we end up with a +1 charge. Now, with oxygen, so now that we're over here, we've got carbon with 4 bonds, starts with 4 electrons, the formal charge is 0. Over here, oxygen starts with 6 valence electrons. We have 1, 2, 3 bonds, so that puts us down to 3. We have 2 lone pair electrons, so that puts us to a +1 formal charge. Now, the question is, which is more stable? And what you have to ask yourself with stability is a few things. First of all, does everyone satisfy the octet rule? So if everybody satisfies the octet rule, we would say that this is the more stable structure. If everyone satisfies the octet rule, the next choice is to look at where the charges go. So if we end up with a charged molecule, we want a negative charge on the most electronegative element, and we want the positive charge on, we're going to say carbon. Even though hydrogen is the least electronegative, it's going to be hydrogen. It's going to be carbon. So we want to put the carbon on the least electronegative element, most likely it's going to be carbon. So if we look at the structure on the first homework question, I draw the structure. And let's see here. We got hydrogen, hydrogen, hydrogen. We're going to put our lone pair on oxygen, and we're going to put a positive charge on it. Save and exit. And I'm going to say the one that's more stable is the one that satisfies the octet rule. So I'm going to say the new one. Let's see if I'm right. Yep. So let's go to the next one. So here we have a lone pair being pushed over between the two. So what we're going to do when we do this, let's go ahead and just draw out our atoms. Hydrogen, carbon, nitrogen, hydrogen. We're going to convert this double bond to a triple bond. So by taking that lone pair and putting it between the two, we're saying that's forming another bond. 3. Oh, that's right. Now, what about the formal charges? Well, we have carbon here with 3 bonds, starts with 4 valence electrons, so 4 minus 3 gives you that plus 1. Here we have carbon with 4 bonds, so it doesn't have a formal charge anymore, but we still have to finish with a positive charge. So when we do this, and we count it up, nitrogen's got 5 bonds, it starts with 5 electrons, finishes with 4. That would put the positive formal charge there. Now, the other thing is your formal charge, quick hint, are going to move with the resonance. So it's not like this carbocation, this formal charge of plus 1 is going to end up like somewhere else completely different on the molecule. It's probably going to end up with wherever you move the lone pairs to. So we do a save and exit. Now, which is more stable? Well, here we have nitrogen exceeding octet, so this doesn't work. And here we don't have carbon satisfying octet. So octet rule we're going to break regardless. The next step is to say who's the more electronegative element. So nitrogen is more electronegative than carbon, and because of that we would rather the positive charge reside on the carbon and not the nitrogen. So I'm going to say here that the original is the more stable one. And if I check my work, remember that the structure where heavy atoms have a full octet of electrons, but it does have a more full octet. What? Why? Oh, I'm sorry, nitrogen does have a full octet. That's entirely on me. Nitrogen does have an octet. Okay, so yes, I'm sorry, that's a mistake on my part. Here, nitrogen has starts with a full octet, it finishes with a full octet, carbon finishes with a full octet, so what's really driving this is the octet rule again. And those of you who have me for Chem 1, it's really the octet guideline, but here we are. So here we have two arrows. 1, 2. So let's go ahead and draw on all the atoms. Hydrogen, oxygen, carbon we don't need to draw in, nitrogen, hydrogen. So if we look at the structure, our first one is going to convert a lone pair to a bond, so we end up with a double bond between the carbon and the oxygen. We also have 2 lone pairs that remain, so 1, 2. With carbons, when we draw this bond down, we're converting a double bond to a single bond, and we're putting an extra lone pair on nitrogen. So we end up getting 1, 2. So the question is, where are the formal charges? So if we look at oxygen, it starts with 6 electrons. It's got 4 lone pairs and 2 bonds. That puts us to a formal charge of 0. Carbon starts with 4 electrons. It's got 4 bonds. It goes down to a formal charge of 0. Process of elimination, your nitrogen is going to take the negative, but we want to prove that. So to prove it, nitrogen starts with 5 valence electrons. It's got 4 lone pair electrons and then 2 bonds that will put us at a -1 formal charge. So the question is, who's more stable? So let's go through the octet again. So we've got, with the 6 lone pairs and the 1 bond, oxygen has an octet over here too. Carbon has an octet here, and carbon has an octet here. Nitrogen has an octet here, nitrogen has an octet down here. So since both of these satisfy the octet rule, the next thing is charges. So who's more electronegative, nitrogen or oxygen? Well, if we look at it, oxygen is more electronegative than nitrogen, so we actually think the original structure is going to be more stable because the formal charge here is carried on the oxygen, not the nitrogen. And if I check it, that ends up being correct. And it looks like from there, it asks you about formal charge. I don't think there's much more about resonance in here. But yeah, that's also why I gave you the homework on the formal charges as well. It's more not because you're going to be dealing with nitrogen and oxygen on the homeworks or on the exam. It's mostly to kind of get you back to understanding the formal charges so you can quickly do them. But yeah, that's how resonance works. The reverse, I'll show it to you. Because the examples you're seeing there, you kind of saw one, but I just want to make sure it's clear. So let's say we start with ethylene. And I draw an arrow that looks like this. So what I'm saying is I'm going to take a bond and convert it to a lone pair. So what I'm going to get when I finish So now to work out the formal charge. Well, the starting molecule had a formal charge of 0, so everything else in here needs to finish with a 0 when we add it up. So carbon here starts with 4 electrons, finishes with 3 for the rebonds, so that puts you at a +1. Process elimination, that carbon is -1, but you can work it out because carbon starts with 4. It's got 3 bonds, so we subtract 3, and it's got 2 lone pairs of electrons, which gives us a -1 formal charge. Other questions? Can you explain how a simple reaction of alkanes work? Do you know where to put the Br2 molecule in a given alkane? So what you're going to find written a lot, particularly on my problems, books will be kind of sloppy about this, is, let's say we have a molecule that looks like, okay, we'll do this one. And we have Br2, and the big thing we're going to have to do here is light. And the reason we need light, wow, that's upside down, is that it's going to split our bromine into what are called bromine radicals, Br dot. So bromine has an unpaired electron. Well, two things are going to happen. One, this bromine is going to react with a hydrogen. And if we look at a CH bond, this is where you can see, I had a student call this morning the fishhook arrows. It's a half arrow. So what happens in the half arrow is that we split the bonds in half, and we're going to end up with a carbon radical. Now, carbon radicals have varying degrees of stability. So if we have a CH4 group and we make a CH3 radical, this is not as stable as a CH2 radical. So what we would consider a primary. So this is a carbon, this was a CH3 group, and we've removed a hydrogen, so now it's a CH2. So this carbon is bound to one other carbon. So this would be a primary radical. Next up is if we have a carbon with two bonds and a radical. And then finally, our tertiary carbons, where it has three bonds and the radical. So when we make a radical, we're going to make it on the most substituted carbon. So if we look at this molecule, if we were to form a radical here on the methyl groups, it wouldn't be as stable as a radical formed here on the CH2, and those would not be as stable as a radical formed here on this tertiary carbon. So the first thing we're going to look for are tertiary carbons, and if we have them, that's where we're going to do the substitution. If we don't have tertiary, we're going to look for secondary, and if we don't have any secondary, then we're going to react primary, and if you're not reacting primary, you're reacting methane, CH4. So you're going to do a substitution on a tertiary carbon first. Now, as I talk about in the notes, there is an issue with this is called free radical halogenation. So let's say I do my first bromination, and I have a second bromine radical that shows up, and now it pulls off this hydrogen. Well, now this is a tertiary carbon. So my next substitution won't be on this carbon, it'll actually be on this carbon again because I've converted it from a primary or a secondary to a tertiary carbon. So with free radical halogenation, it's very hard to control. You actually end up getting a mixture of different substitutions, and that's why you'll see on the characterization parts of the packets why it says, okay, that's why you had to run the mass spec to figure out how many substitutions you've got. But always, if we have, you'll see it written a 1/2 Br2 or one equivalent of Br2. What this is meaning is that we're only going to do a single substitution. So we're going to pretend that we have this type of control over the reaction, and we're only going to replace one hydrogen with one halogen. The one we're going to replace is on the carbon that has the most substitutions, and if we have, for whatever reason, this molecule has two secondaries, the only thing we can say is we're going to replace one of the secondaries. We can't necessarily say which one we're going to replace. So if for whatever reason this had like a functionality like that, we can't say which of these three secondaries are going to get replaced. So typically the problems are pretty clear as to which one's going to be replaced, or you have some high degree of symmetry, so it doesn't matter where you do the replacement. You're welcome. Other questions? Also answering some questions in chat as well. Other questions? All right, now I got the Oscar Schmidt for the next 20 minutes. It's a little bit out too. Sharp. There we go. Oh my goodness, my hands are dried out. dare you interrupt banjo time. Sure, we'll do number 16. A certain hydrocarbon has a molecular form of C4H6, where the following is not a structural possibility for this hydrocarbon. So, contains one ring and a double bond. Let's just draw them out. So the smallest rings we can form are 3-membered rings. We'll have to consider the 3-membered and the 4-membered. Actually, tell you what, let me teach you the easier way to do it. So a saturated hydrocarbon has the formula C4, or SCN, H2N plus 2. Now, we're going to subtract 2 off for every ring. And we're going to say double bond, but we can definitely do triple bonds and things like that. So if we have C4H6, and the 2N plus 2 here would be 10, so, I'm sorry. Yeah, we're going to subtract off 2. So we actually have 10 versus 6. We have 4, so if we divide 4 by 2, this tells us that we have 2. We either have 2 rings, a ring and a double bond, or 2 double bonds, or a triple bond. So if we go through the list here, contains 1 ring and 1 double bond, that meets our criteria. Is an alkyne. An alkyne has 2 double bonds, that works. It has 2 double bonds and no rings, that's a possibility. It's a cycloalkane, meaning that it doesn't have a double bond, so that's not a possibility. Wait, what? Contains 1 ring and 1 double bond. That's correct. Is an alkyne. That's correct. Contains 2 double bonds and no rings. That's correct. It's definitely not a cycloalkane. Carbon, CH2, 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 that's correct. Let's try again. C5H8. Okay. Oh, which is not. Oh, I'm sorry. I thought it was asking for which one is. Oh, yeah, there it is. So I was correct for the wrong reasons. If you invert what I put, you would be correct. So let's try this one. C5H8. So for C5H8, yeah, I'm drawing all. I was like, yeah, these are definitely possibilities. Oh, it makes sense. Which one's not? I'll learn to read and follow all directions. So C5H8. The formula for a saturated alkane here would be 5 times 2, which would be 10, so 18. So we're missing 10 hydrogens to be saturated, so we divide this by 2. That tells us the number of pi bonds. So pi bonds, double bonds, triple bonds, and rings. Has to equal 5. So we'll go through the answers. It's a cycloalkane. That's definitely not a possibility. It contains 1 ring and 1 double bond. That's not a possibility. It's an alkyne. C5H 10, 12. Oops, sorry, not 18. 4. Can't multiply right now. Sorry, read to the math. So if it's C5H8, a saturated linear alkane would be a C5H12. So we need 4 additional hydrogens, or pull off that, divide by 2. That means that we have 1 pi bond or 1 ring, 2 pi bonds or 2 rings. So it's definitely not a cycloalkane. It can contain one ring and one bond. It can be an... Wow, these are literally the same answers. It is an alkyne or contains 2 double bonds and no rings. Oh, that's surprisingly uncreative. But yeah, that's basically how you would do those. So take your formula for a saturated linear alkane. Subtract the number of hydrogens between your formula and the actual... you subtract the number of hydrogens in the theoretical linear alkane by the number of hydrogens you have, divide by 2, and that gives you the sum of pi bonds. So pi bonds are single bond, or double bonds and triple bonds, and the number of rings. Drop question 17. Other questions? Little cord. Glad I could help. I've got another 8 minutes. What are the questions y'all got for me? So we got less than 10 minutes left. Just a reminder, your homework is due tomorrow at midnight and your exam is due Sunday at midnight. So email me. I'm kind of around this weekend, but definitely if you see a question on the exam that you think is really completely out of left field, shoot me an email, let me know. I'll take a look at it. And otherwise, Oh, next week we are off Monday and Tuesday, so there's no live stream Monday. It's technically fall break. I say technically because you're in an online course. It's not like you physically show up. But those of you in the Tuesday labs, we don't have lab next week. Thursday, if you're in Orgo 2, you still have lab next week. Thursday, if you're in Orgo 1, it's a review session if you want to show up. I'm there to answer any questions you might have. Otherwise, try to keep up. Next week, we start the new Test 3 material. So I will see some of you next week, but definitely probably the week after that. So thanks for showing up.